welcome back. It's good to see those of you who are here today. And we'll let people trickle in as they come. Where we left off on Tuesdays, we were looking at some of the line rasterization and then connecting that to triangle rasterization. And I know the teams are very busy doing their best, working on that in the lab. And there's no substitute for doing. So you'll be doing it and you'll find out all the very clean algorithms have all sorts of weird edge cases, including the one that you are implementing. So this becomes a little bit of a hodgepodge of a topic. So assuming that we have quote unquote covered rasterization, and I'll be excited to see what you come up with. Um, I want to talk about some of the other things that just happen in the pipeline, and that's why this is kind of as I said, a hodgepodge topic. So other things that can be done, knowing all the work that's required to rasterize triangles. Um, Other things that can be applied before we get to that point to maybe minimize or reduce the total amount of work that's required. That phrasing isn't quite right in terms of reducing the total amount of work. Part of what we talk about when we talk about clipping and culling to start with here, and then hidden surface removal next, it's not really necessarily about work reduction. It's more of a correctness thing that, as we'll see, that as we specify objects and those objects uh, aren't necessarily fitting into the scene that we're wanting to draw, we shouldn't be drawing them. So you can think of it as a reduction of work. That's a valid way of considering it, but it's really more of a correctness issue as well, which is what do we do when we're trying to rasterize something and we realize we shouldn't have had it be visible at all. So partial work reduction, also more of just a general correctness issue of what do we do when things don't fit inside the window we're interested in, and that's what this picture is attempting to start a sort of show here, that you have your scene and it's got a collection of objects. And let's not worry too much about how this particular object was created as just an arbitrary kind of geometric looking shape here. That you have these coordinates that are specified, right? And we have our vertices, and eventually we're filling in shapes based on what we have specified for our vertices. But when we display that scene, whether we're talking about the vertex transformations we haven't really covered much in class yet, or even just thinking about like the viewport transformation itself, we have this idea that we have this sort of infinite range of which we can specify our vertices in and our corresponding primitives to fit inside. But then we have the actual window we want to draw into. So you can think of it as being things that lie outside the range -1 to 1 in the x and y dimension, or just things that are outside of our window for the window coordinates we're interested in drawing here. Um, we can easily have a scenario in which we specify geometry that isn't actually supposed to be displayed on our resulting screen in our resulting window here, and that's what this is trying to visualize here. That when we display that particular scene, only things that are in that particular window should be the ones that are displayed. So when we refer to the word clipping, the analogy is meant to be made to using a pair of scissors, right, and to clip things that shouldn't be displayed. And I would also again say that it's not an optimization thing in and of itself, although it is. It's also a correctness thing. If we have specified this window and that geometry for our particular scene in our window, we should only see what is remaining. So it does also save time. That's less things we have to fill, less fragments we have to generate. So it is a performance optimization as well. But at some point, we have to have a method in which we're only actually drawing what is inside that window. And this part of the graphics rendering pipeline is referred to as clipping. And so think of it like a pair of scissors. Something is outside our box. We have to then clip and get rid of what is not meant to be displayed inside that window. Um, I think it's relatively straightforward approaches we'll talk about here, but also with some edge cases that make it a little tricky on the periphery. No pun intended. So we could start with line clipping. There's lots of different approaches to line clipping, but some of the very original ones from the 1960s are still the ones that are basically in use today. It's good to start with lines first, and then worry about other primitives second. So if we're doing line clipping, in this case it's lines and points, we should be able to know it when we see it, right? That based on what's being specified here, our vertices or points P1 through P10 here, we should know what the quote unquote correct output should be. That certain things should be removed, right? We've specified P1. Well, that's inside our window WX min, WX max, WY min to WY max. We should keep P1. Whereas P2 is outside of it, right? It's something that shouldn't be displayed on the screen. When we're doing the clipping, at the very least, we should be, getting rid of P2. Likewise, that line is disappearing quickly for us here, P3 to P4, we should be getting rid of that as well. It's an entire line, and we have to calculate when that circumstance is actually happening, but just looking at it and looking how it would display, we can see that line P3, P4 and say, well, that also should be gone. We shouldn't actually be drawing that. We shouldn't even worry about rasterizing that particular line. Then there's the edge cases. I'll stop it with the puns. But there's P7 through P8 here, right? If we look at P7 and P8 individually as just individual vertices, we would say, well, we should get rid of it because they're outside that window. But even though they're both outside the window, and we can look at P9 and P10 as another edge case here as well, for P7 and P8 at least, even though those individual endpoints of that line segment are outside the window, when we're actually drawing it, we realize that that's corresponding to a primitive that a good chunk of it or some portion of it is actually inside the window. So for the clipping operation, it is as if we're taking a pair of scissors and cutting everything that would wind up being outside the window. But unlike with a pair of scissors, we want to avoid having to draw everything and then to somehow like erase the things that are outside the window. We want to have approaches that allow us to specify for input vertices that are specified. Let's modify those vertices. Let's drop some entirely, but let's modify the vertices so that the resulting geometry that we're drawing to the screen is going to correspond to something that would have been the case if we had specified those points here and here versus where they were before we dropped them here and here. And same with P9 and P10. We want to clip it to the boundary of that window so that it's equivalent to a scene in which we'd specified a vertex here and a vertex here, and we would just be able to rasterize that shorter line instead. So some of those cases are easy, or at least relatively straightforward. If we're just doing point clipping, so GL points is what I'm referring to here. We just have to check the bounding box, right? If it's in normalized device coordinates, we're just literally checking -1 to 1 in our X dimension and Y dimension. We'll talk about Z as well in a moment here. And we know it when we see it, but then the math is also pretty simple. It's two comparators. So for every point that comes through, check if it's within the range of X and if it's within the range of Y, we're good. But if either of those is not true, we're getting rid of those. So we know it when we see it. It's kind of obvious, I guess. But in this case, the math as the actual computation is also relatively obvious. For lines, I already talked about a couple of those special cases, right? But we can think of it in terms of looking at each endpoint individually. If both endpoints of a GL lines are inside the window, we're good. We continue on. If we have one endpoint on the line that's inside the window and one that's outside, we're also good in the sense that we know we have to clip. We know it's a partial line segment that we're going to wind up wanting to draw for that particular line that's specified. Where things get a little tricky, even though, at first glance, it's obvious when you look at it, well, we have to have the math that allows us to automate this. But when both endpoints are outside the window, we have to take a little bit more care to determine, does that mean it's completely to be removed, or does that mean we're going to get a partial line segment? And that's that third case, is the slightly trickier example here. As with everything, we can have a brute force type of approach. For those lines that have one endpoint inside the window and one side outside the window, one inside, one outside the window, we could just calculate the intersection point, which is not that hard to do because calculating the intersection of any two arbitrary lines requires some division potentially. But when you're clipping against, in this case, horizontal or vertical lines where it's just a constant, it's a relatively straightforward thing. So that's one such approach. That's not so bad if you have that case where one point is inside the window and one point is outside it. When we have both sides being outside, without some additional assistance here, then it becomes a little bit costly, at least relative to the previous case. That, well, again, you look at it, you say, I know exactly which edges to compare against, but it's not that obvious as the vertices are coming in. So the brute force approach to doing that type of line clipping would be to say, for each of my endpoints, if they're both outside our bounding box or our window here, we would have to do an intersection test with all of the lines here, and that becomes a little bit painful. And it's not necessarily an issue of being much too slow. It's the same thing we mentioned on Tuesday with regards to rasterization. uh, Speed is a little bit less obvious to reason about with regards to these kind of things. But it is definitely involving more floating point math than it would otherwise need to have to do. So one of the fundamental algorithms for doing clipping, specifically for line clipping, but there's variations of it for other primitives as well, is the Cohen-Sutherland clipping algorithm. And I think it can be the case that when you read about one of these things, historical innovations in computer graphics or just computing in general, I think it can often be the case where your takeaway is, well, that's obvious. And maybe it is, but oftentimes it's obvious in retrospect. And oftentimes also um, approaches for which the innovation wasn't just a clever little hack. It was a necessary thing to be able to implement this in the hardware realization of the time, right? So when I talk about this, I think it's okay if your thought was, well, if I was forced to come up with something, I'd do something very similar. Maybe so. Um, Maybe so because there's been now generations of people coming up with similar approaches to these type of algorithms. So it's simple and it's straightforward and it's basic, and those are all good things. And it was foundational to be able to do this kind of clipping. So for the Sutherland clipping, what it does is essentially tagging each of the individual vertices with where they fall in the world coordinate system with a 4-bit code. So it's relatively straightforward here, but you would have a 4-bit region code where, and it could be ordered in any direction, but each of the bits correspond to where that point is relative to that particular boundary. So there's the left boundary of our window. And if the vertex is to the left of that left boundary, it would have a 1 in this position. And then there's a right boundary. So it would be a 1 in that position. Then the same for the top and for the bottom as well. So for points that are entirely within the window, they would have a region code of 0000. And you could see that you would never have more than 2 bits of that region code be 1 at any given time. For an individual vertex, you can't be both above and below the window. You're either above or below or inside the window. Same for left and right. So it basically just divides the entire world into the 9 different regions here and assigns a code corresponding to it, where 0000 is entirely within the window, and then based on whether it's above, below, left, or right, you have the corresponding bit associated with that particular vertex. This simplifies some of the tasks of, yes, we know it when we're looking at it, but just based on this assignment of region codes to the individual vertices, this simplifies some of the tasks necessary to be able to do um, that type of clipping. So we would take every endpoint and we would label them with the appropriate region code. So again, back to the previous example here, and that should be a relatively straightforward thing to do. We already have to have the comparator logic to the bounding box or to our window that we have here, and based on the results of those comparators, you would then be just setting the individual bits here. So just taking P11 for example, we did right, left, bottom, top. So we must have done left, right, bottom, top. This point is to the right and above our window, so we get 1010 corresponding to it. P12 is not above, but it is to the right, so we get 0010 here. So we first start off and we just label the points with the corresponding region code associated with it. And that at least lets us know very quickly, well, if we have 0000 for both of our endpoints, we're good. We are done. We don't have to do any clipping at all. Let that primitive pass on. So far, so good. What this labeling also allows us to do is that if we do an AND operation and we recognize that both endpoints lie to the same extreme for either top, bottom, left, or right, we can entirely remove those lines. Again, it looks obvious when we see it here, but in this case, for those 2 points, P11 and P12, they both have a 1 in the same bit position. A simple AND gate there could tell us that that's the case, that yes, they both lie to the right of the boundary, and um, consequently, it's all entirely to the right of the window, and it's never crossing back over to the window. So for those that we can't immediately classify as being entirely within the window or entirely with outside the window, um, we would then be doing that endpoint comparison again, right? So we could compare those endpoints outside the window to that boundary, and you could choose whichever order, as long as I think you do it consistently, it would work. And then you would generate a new point based on that intersection. And then you would check based on that intersection, is the resulting line segment entirely inside or outside the window? If it's inside the window, you're going to have that partial clipping. If it's outside the window, you can then discard at that point. So it's effectively the same approach as what I was mentioning previously. Of you have to do the intersection testing and check, in fact, that the resulting line is going to be inside or outside. But in this case, by using the region codes, you can tell exactly which intersection tests have to be done relatively quickly. And you can also determine for the resulting line what the region code would be for those points, and then very quickly determine whether you need to continue checking or whether you can be done at that point. I think showing it just in this visualization is relatively straightforward. So if we look at that P9 to P10 below, P9 is entirely inside the window. P10 is below the window here. So we would still have to, based on the region code, we don't actually know whether or not we do know it doesn't cross the left or right boundary. So we would do an intersection test here to get a resulting point P10, which it's on the boundary, but it would have the region code of 0000, and we know the resulting, call it P9, P10 prime, uh, would be entirely within the window, and that would be the resulting primitive. So again, you would want to think of that clipping module as being its own separate pass of the graphics pipeline. It would have to happen before rasterization, right? It would have to happen before we would take the time to actually fill in the points inside that line. Or again, as we talk about triangles, before we fill in our triangles for it. And it would let us know relatively quickly whether we could just completely remove those primitives. So that is a bit of a performance optimization, or we can partially modify those primitives as they're coming in. So in this case, in your user application, in your OpenGL code, you're specifying P9 and P10. What's actually getting rendered is P9 and that P10 prime, based on where that intersection would be with that window. That's what it means to clip something. So that's the case that we said we know would be guaranteed to only be partially clipped. When we have that P3, P4 case, where, again, looking at it, we can see that it's going to be dropped, but this algorithmic approach with our Cohen-Sutherland clipping would start at either ending. So in this case, let's assume we start with P4, which um, has our region code of 1000 because it is above the window. Based on the difference in the two region codes, we know that this line eventually crosses the left boundary because we go from a 0 in this position to a 1 in this position. We don't have to check against all the boundaries. We know that that's the boundary that this is going to be checking against or be crossing. So we would perform the intersection of the line with P4 to get P4 primed, the intersection of the line with this left border here to get P4 primed here. And then the nice thing about this approach is then we're done. We've calculated P4 prime from our P4, and we could have done it in the other way as well. But in this case, by starting with P4, we get to P4 prime. The resulting line segment, we can now quickly check with that AND operation to determine that that's completely to the left of the window now. So we can completely remove that line segment that we have there. Now with that P7 to P8 case, we have to then check. So for P7 to P8, we know we're then going to be crossing the rightmost border here. We calculate P8 prime. That gives us something that's now inside the triangle. Likewise, P7, we have to check against the leftmost border. That gives us P7 prime. Then we get our resulting approach here. So the math is still required to actually check, that we're intersecting with those boundaries. Well, first off, the math for that is not so bad. What Cohen's Sutherland gives you then is the ability to say, I know exactly which border to check against, and I can relatively quickly tell when I'm done. When either I have a resulting line segment that's entirely within the boundary, that's my zeros case, or when I have something that is going to be entirely outside of the window and I can just stop and drop it entirely. We can do a quick example here. I don't think we have to belabor the point too much here. So we would start with a labeling of our points in terms of which boundaries we would have to check. I understand that it's a little not I don't think silly is the right word, but we can do this on pencil and paper relatively easily. So it's hard to come back and say, well, now I'm going to manually do it and get the same result that if I was just using a ruler here. But we could start with our region codes, right? So for this 1014 point, um, that is both. Again, it doesn't matter what I do as long as it's consistent. That is both above and to the right of the point, whereas this point -7, -3 is below and to the left. So we would have to do our intersections. So we see for both the left and right and top and bottom, there's those intersections we would potentially have to do. In this case, we know that since -7, -3 is below the object, we can then calculate this point here. If this is P1, P2, we could calculate P1 prime by determining what the intersection is um, between that line segment and the lower boundary of the window. And you wouldn't want to overthink this. I mean, we could plug it into an equation. The lower boundary of the window is an equation, right? It's y equals 2, right? And likewise, this line segment is also just an equation that we could draw in slope intercept form, or we could represent in slope intercept form. For right now, I think we would care mostly about the slope to be able to do that intersection. Um, we have a rise of 17 and a run of 17. So this line segment itself would have a slope of 1 for that particular line. So given a starting point of -3 in the y dimension, um, plus the difference in our x dimension between this -7 to this location we would have here. We start with, I'd have to do it in the y dimension. We start from -3, we're moving up here. We know that the resulting point that intersects would be moving up 5. So we are moving over to over 5. Would be -2, 2, which would be a point that would have a region code of all zeros. Likewise, now we would then have to look at the other side of this and its intersection with the right-hand plane here, which is just an equation of the form for this one is just x equals 4, right? It's not exactly drawn to scale here, which is why it looks a little misleading. But we know that with our slope of 1, to get down 6, we also have to get over 6. And so our intersection would be 4, comma 8. And I could, it's obvious because you look at it because we intersected with the lines, but we can actually then check the region codes, determine that we have 2 points that both have region codes of all 0, and we're done. We get the resulting vertices that are um, provided for it. In this case, you would also have to test that as well, Riley. So because it's crossing both the left side and the right side and the top and the bottom, you would be checking against all 4. So we could do that, right? This would be this is over 2, so up 2. So this would be -5, -1, which would have a region code of 0100. And then this one, we would also compare against this one here, which would be down 4, so that'd be 610 with a region code of 0001. So we'd have to continue. So it doesn't, I mean, yeah, it's a good catch. I mean, the way I did it, I compared first against the region code that gives us a completed result. We would compare against all four, because in this case, we're crossing all four boundaries. And we would stop when we had either something that was guaranteed to be outside, entirely outside, or guaranteed to be entirely inside. So that's true. I skipped a step, but if you chose them arbitrarily, we could have chosen those two first. So you definitely want to think of this module, sort of your clipping module, as part of that pipeline. Just like we have our viewport transformation and now our rasterizer. This would happen earlier. It would happen. In this case, it would likely have to happen after primitive assembly, but then before the rasterization, because we have to know we're operating on lines here versus operating on triangles or points. Because how we would do the clipping would be different, right? If these were instead specifying points, then we'd be discarding them entirely, right? So the way we provided MP2, we'd have to kind of rip that back out. It wouldn't be that hard to do, right? I mean, primitive assembly is pretty independent from the rest of the MP2 code base that you have, but we would have to assemble the primitives first to know what they were intended to be, and then we would apply this clipping, in which the input output relationship would be a little bit interesting, right? Because in some cases, you would get input primitives coming in and nothing coming out. And as we'll see, in other cases, you'll get input primitives coming in and modified primitives coming out. And then yet in some other scenarios here, not for lines, but when we look at more two-dimensional shapes, you'll get input primitives coming in and multiple output primitives coming out for that one individual primitive here. So I think hopefully that answers your question. How do you know? Well, we don't know. We have to test, in this case, all of them. I know because looking at the picture, I knew that we would get the completed result by just testing against those two edges there. So that's Cohen Sutherland. You've now gotten your history lesson for the day here. We have to do the same thing for areas, and this picture is just for illustration purpose. We've already talked about how for a lot of the approaches that we want to apply to our graphics rendering pipeline to actually work in practice, we want to have convex polygons. So we're not going to be specifying star shapes as our input polygons to the system, but just to visualize what it would mean to do clipping in actual areas, this is pretty useful for that. Again, we wouldn't specify this as a single primitive, but still you could see what would happen. It is the scissors type of approach, right? Where we're applying the object that we want to render for our scene, and we're cutting out the shape corresponding to what is resulting. So for lines, we either get nothing or we get a line back. For areas, it's a lot more tricky than that, at least in terms of what the resulting scene will look like, because we may have something that has a certain shape to it, and even for triangles, this will be the case. I can already see some of you drawing it out, on the side, which is great to see what weird things can happen to triangles. You'll get a shape that doesn't look really anything like that shape, and not only will you get different primitive shapes, the resulting vertices that you'd want to need for those shapes is also potentially going to change. Right? For a line, that's not the case. Line is 2 points. We're either getting rid of it entirely or we're going to have a line resulting. We go from 2 points to 2 points no matter what here. For our areas, and again, we're not going to be providing this. We're not going to be providing these input shapes to our pipeline, but you can already see how it looks totally different, right? So the number of points that would be corresponding to those primitives would change fundamentally. Um, right. Well, we could always, in our pipeline, and I'll say the OpenGL rendering pipeline, um, we could always provide these type of shapes, but just not as a single primitive. So, and when we talk about clipping, we'd be doing it on a primitive by primitive basis here. None of these would work even in old school OpenGL where you could specify arbitrary polygons, they wouldn't work either. You'd get results that it would really depend on the implementation. Would probably turn it into a concave version of it, or would have weird overlapping triangles. Um, but I think it's fine, even ignoring the oddness of the shape. Something I want you to kind of start thinking about a little bit is even if we were just doing this triangle as opposed to the rest of the very concave looking shape here, we do need to apply clipping to it. And so in this case, maybe it's not so bad where we start with a triangle and we end with a triangle, but we're modifying multiple vertices in that triangle to get one which is um, aligned with the bounding box. Let me draw a different one just very quickly to I think better explain why this starts to get a little bit more tricky in the case of area versus lines. See what I can do here. If this is our window, looks sufficiently windowy, and this is our triangle that we're specifying, right? Nothing's stopping you in the application from specifying any triangle you want. There we go. That's a triangle. The resulting primitive that should actually be drawn. In terms of a correctness thing, again, maybe it's saving work in terms of not rendering fragments that we shouldn't be. The resulting triangle that should actually, or the resulting shape that it should actually be drawn would look like this, right? Would actually be a trapezoid. Close enough. That's tricky. That doesn't tell you how it's done, but just conceptually, I think just thinking of your SGP lab designs, that's now a tricky thing, right? We specified triangles. Triangles are well behaved. Triangles are boring. They're 3 points, and we render our triangle. We've gotten out a trapezoid. And so, what does it now mean to actually render that trapezoid? We haven't built, and we won't be building, and we generally don't have trapezoid rendering hardware. And there's other edge cases as well. That's also a relatively well behaved edge case, but there's other weird things here. Yeah, absolutely. There would have to be a mechanism. Well, you can do it in two triangles, but yes, there would have to be some mechanism by which we would be able to take that resulting shape and recognize that now instead of just being a regular triangle, we would then have potentially two triangles we would actually have to pass on to our rasterization stage. So clipping itself, it's kind of pitched as a work reduction. This is actually probably more work, right? Incorrectly rendering that initial triangle is going to be less work than correctly rendering the two resulting triangles. And there's more edge cases than that. I think we could draw some in which I'll try here, right? On top of this as well, where for my next triangle, let's see what I can do. I haven't thought about this very very much yet. Nope, that's still a triangle, and it's not the color I wanted to draw it. If I do, oh, this would be fun to kind of draw some edge cases. There we go. That's a weird one too, right? So we want to do clipping on that one. And then again, that's a valid triangle, right? There's all sorts of reasons you'd want to have um, that triangle. That's a great question, Sam, and I want to get to that. The answer is no, and I think it's important to the reason the answer is no. Um, anyway, let me just quickly draw what that resulting weird-looking shape would be. I guess by weird-looking shape, I mean trapezoid again. Okay, so in that case, it's a quadrilateral still. Nope. Someone's supposed to correct me when I make mistakes. Look at that. It's got the extra edges because of how it's not flat when it's exiting there. So now this is going to render all sorts of different ways, right? Now it's going to be multiple potential different triangles. No guaranteed way. I mean, I can't even say for certain exactly how that would get rendered. But now you'd have multiple triangles, 4 triangles, or 3 triangles in that case to render that particular shape. Thank you, Ryan. So great question. Can we just render it and clear the color buffer outside the bounding box? I think in theory that makes a lot of sense. Hey, don't worry about clipping, just draw this kind of thing. And it really depends on what coordinate system you're operating on. And a lot of these approaches would be doing it after all the vertex transformations. So we're reasoning about a positional space in which it's -1 to -1 to 1 1, right? And we've been specifying our input vertices because we haven't done any vertex transformations in that space. But think about what happens after we apply that viewport as well, right? We've now applied that viewport, and then what that would then correspond to, if we assume this is the top of our screen, right? This then becomes our 0 19 19, and this becomes our um, 1079 0 point there. What does that then mean for those things that are outside that range? And where would they actually get put in memory, right? Um, what would it mean to have a location here? What address, you connect that to your render output. What does that actually go into memory? Who is that actually overwriting? Likewise, values going over here. It's think of it as a buffer overflow if you want to, or if I'm trying to draw a point that's out here, even though it's supposed to have been clipped, that's actually going to correspond to something that's going to be on the screen right around here, right? Or some point in the future rows, right? And some of you, as you were testing MP1, may have been seeing that kind of effect, right? Where you were off by one and you were seeing it at the top of the following frame. If we didn't clip, if we instead took the approach of draw and let the memory hardware kind of sort it out for us, you would have all sorts of really weird artifacts. And having said that, we're not implementing clipping this semester. We're going to have all sorts of weird artifacts if we're not careful. It'll be kind of fun to test and see what happens here. Um, it's a great question, Brian. I don't have a specific answer. Oh, Steve provided an answer to that. It's always a trade-off. Speed is paramount, I guess, and then adhering to a spec within reason in terms of complexity of the design. These designs are pretty horribly complex. I mean, there's a reason the teams, and there's multiple teams, and teams not just looking at this generation hardware, next generation. They look at the generation after the generation of that hardware, because they do get pretty horribly complex. And when you, as a consumer, are buying the next GPU, you don't really care how complex it is, right? You care about its characteristics, how fast it is, how expensive it is, what the power consumption, thermals, and other things are. So complexity or whatever it takes to kind of win the day. Um, there's a different discussion about the trade-offs behind having more or less complexity of the individual components and then being able to scale it up more or less based on that. And Ryan, I don't actually have the answer, so let me know um, if you come up with something while we're going through lecture. I don't know the answer of given an arbitrary clipped triangle, how many resulting triangles we could be guaranteed to have, or the upper limit of it. Let me know. Right. The bound. Okay. Yeah. So the bounding box is that -1 to 1, or the world space we're specifying here, and it is ultimately going to correspond to a viewport, which may not be our entire screen. Right. If you ran that viewport application, the viewport is whatever subset you want it to be, but we still want to make sure that nothing's getting stored in memory outside of what would be corresponding to that window. It was a great question. I'm really glad you asked it. This is a little hard to see with the colors and the overlapping, so if you're bored, draw some triangles out. Implementing clipping is very much a valid thing if you want to do for your class project. I know we haven't talked about projects yet. I didn't want to complicate things. Let's see how MP2 finishes up, and then we can introduce the projects and what I was hoping for. But my goal for the teams was just to propose something that extends upon what we have in some reasonable, both meaningful way, and also not an overwhelming amount of work to have to be done for it, right? It's basically twice the length of a regular assignment in this class, so your complexity should be less than twice that of a regular lab, because I'm not providing you the guidance, I'm not doing the starter design for you, and there's no write-up associated with the introduction. But something like clipping would be very doable. um, You'd have to really You'd have to really think through those issues though if you really wanted it to work in practice. Um, there's a thousand different project ideas. They're all fair game, but my job I think will be to kind of scale back ambition more than anything else. Right? You'll have 4 weeks. Um, you'll have other projects as well in other classes. 4 weeks. It's open ended. Um, but be honest with yourself in terms of what as a team you'll be able to accomplish, and something fun to show off, fun to demo. It'll be really fun to be able to do that. All right, we lost the plot here briefly, but so just like the Cohen Sutherland algorithm, there's same guy. Sutherland's name, Ivan Sutherland, keeps coming up over and over again in the history of computer graphics. But the clipping algorithm for this, at least at first glance, is obvious, but it's looking at it at a vertex by vertex basis, and then considering that vertex in turn against the boundary. If the vertex is already inside the boundary, save it. For the ones that are outside the boundary, we go and we progress from point to point to point, and we then calculate that intersection like we were doing for the line, and we're just basically saving that point as the new vertex corresponding to it. So if we start here, this point is out. As we go from here to here, we clip and save this. We also save this. We then go from here to here, we save this point. We go from here. Oh, you can't see where my line is. Let's try that again. Um, Starting again. We're going from vertex to vertex and calculating the intersections again in the same exact fashion as we would do so for that line clipping example. The only difference is um, we are saving a potentially modified number of vertices as the output. So the input is a shape, and it wouldn't be a star, but in this case for visualization, it's fine. The input is a shape with a set of vertices associated with it, and the output is a new set of vertices. So we go from vertex to vertex, and we calculate those intersections. So we start here, and it doesn't matter which one we start. We start here, and we go to the next vertex, and we would then save this point, that intersection point. This one we save because it's inside. We go from here to here, and we save the intersection point. We then go from here to here, save the intersection point, and so forth. So we're tracing the shape effectively, calculating the boundary conditions and the intersection points, uh, basically the same exact way we were doing it before. You have from vertex to vertex, even though it's corresponding to the edge of a shape, we still have a line segment associated with that. We would be calculating the intersections with those same exact line segments. And then we are saving the points that wind up resulting and being inside our bounding box here, our window, and that would be the resulting shape. So it's something of a natural extension of the line clipping algorithm. The difference is we have to have an algorithm that can then rasterize the resulting shape. So that part isn't really covered as part of the Sutherland Hodgman itself, but at least it gets you a set of vertices corresponding to a shape. And the assumption is um, if you have a convex shape as an input, as in this example here, you will still get a convex shape as an output. So the same kind of approaches for rasterizing the resulting shape should still work. It's as going back to our drawn version here for our MP2 hardware that presents some problems potentially. If we're rasterizing triangles, and we've done primitive assembly, and the output of the assembly is a triangle, we now would have to have some module that, call it primitive reassembly or some such, right? Where 3 points come in a triangle, an increased number of points come back out. The shape got a little ugly here, but at least we know it's 1, 2, 3, 4, 5 points come out in that case. In this case, it was 1, 2, 3, 4. In other cases, it will just be 3. Um, it'll never be 2, I guess, right? So 3 or more. If someone draws one that has 6 points, I'd like to see it. But anyway, this one would have 4. This one would have 5. And we have to be able to rasterize that resulting shape as well. So we would have to find some method of decomposing that back into a triangle strip or some other set of triangles that you can rasterize it. So the clipping algorithm itself doesn't or it's somewhat orthogonal to how we actually draw the resulting shape. But otherwise, the Sutherland-Hodgman proceeds very similarly to the line one. So in this case, if we start from S and make our way to P, both points are inside. We can save point P. We then go from this point to the next point here. We would then not save this next point. We would save the intersection point. But we would continue on with that point to do our intersection testing. We wouldn't save either of those points. Finally, we would continue with this point, go back to that final point, and save that particular point there. It gives you the effect of that clipping, that cutting against the object that we have there. And the end result would be, in this case, for a convex quadrilateral with 4 points, we wind up with a different one with 4 points back out. Assuming that we were able to rasterize this in the first place, we should then also be able to rasterize that result. And it's one in which we're guaranteed, the points correspond to the viewing region we actually have of interest for that particular viewport and application we're trying to render. It's a lot harder to visualize, but when we extend this to 3D space and we're doing vertex transformations next, and it'll be fun. It's a perfectly fine topic. We get to high school math for that topic. Um, and it does involve processing in the third dimension, the Z dimension here. It turns out that while the clipping shape is a little bit more complicated there, it could be a parallelepiped, it could be a cube, if nothing else. The same approach can apply. That in fact, it's easier to draw it when it's happening in 2 dimensions, but it's just an additional dimension. We can apply the same exact concept. We can have region codes. We can determine where we're crossing the intersections of those planes, uh, doing the same exact thing in the 3 dimensional case, where we haven't talked about this at all yet, where you have sort of the camera analogy of I have vertices in a scene. Where am I looking at the scene? Or I have primitives that I'm wanting to draw for my scene. Where's the camera or the human eye? Where am I looking at the particular scene? That dictates what things should be clipped or not clipped in that 3 dimensional view of things. So we wind up, if this is our input geometry we're specifying for the scene, based on where we're pointing the camera, we're actually wanting to get rid of those some things. They're either too far away, or they're behind the camera, or they're too far outside of the field of view of that particular camera to view. Doesn't exactly say how we do it, but the end result would be that kind of clipping result where we're dropping a lot of those things, but it'd be the same exact computation that would be happening. So based on what our viewing volume would be versus our viewing square, for a 2 dimensional analogy, we would just check: am I entirely above the volume? Am I all the way to the left of the volume, and so forth, and compare against those edges. Um, so the example we had, which I am not sufficiently artistic enough to be able to draw in 3 dimensions well enough, where we're seeing our triangle resulting in 3 possible points. Um, it gets a little bit messier because now it's a cube, right? That we'd be checking against that, because there's also that depth dimension, that Z dimension of our geometry here that we're specifying. We have to check against, at the very least, not just the four potential edges here, but we would have an actual, at the very least, a cube and 6 sides of a cube we would be checking against. There can actually be a non-cubic structure depending on the perspective of the camera that we're specifying, but at the very least, we're checking against a cube. But the same kind of intersection tests work for that approach. I've mentioned that, yeah, the order in which that type of topic gets introduced, opinions vary. This picture, I understand, it doesn't make that much sense to you. Next week, it'll start to make more sense when we start talking about what the processing of vertices implies, what we're trying to do as we translate and transform these vertices. We'll also start with the 2 dimensional view of things, because it's just easier to draw, and then we'll just extend it to 3 dimensions just by looking at how the math would then change for the third dimension. Also, when we're in the third dimension, though, there's another aspect of this. So um, we're doing a very implicit version of this already via just how we write our software. But we do have to worry about so-called surface detection or visible surface detection techniques. It's also referred to as hidden surface elimination. It's all referring to the same kind of things, where we have multiple things in our scene, and we're in theory specifying a three-dimensional scene where there's depth associated with it. We have to determine what should actually be displayed on the screen. Just like we're specifying three-dimensional things, and certain objects may be outside of what is actually visible at all and should be clipped entirely. This is complementary to clipping approaches that already have to be applied. But what this is attempting to show is we have a cube, a sphere, and a cone here, and depending on where they are relative to each other in that three-dimensional space, we still have to determine, for this particular pixel here, what color it should be. There's not a ton of overlap there, but there's overlap between two objects. Should it be the green of the sphere or the yellowish of the cone here? Again, looking at it, it's obvious what it should be, but we have to determine what approaches allow us to know that even though we have two objects that correspond to the same XY location in our frame buffer, or would correspond to the same XY location in our frame buffer, that this yellow one is the one that actually should be drawn. There's two complementary approaches. I think from our perspective, and certainly in terms of what we're implementing, the image space methods that you'll hear them refer to as just Z buffer methods, is the much more relevant one for us. But there's all sorts of what's referred to as object space methods, and there are techniques that basically correspond to early optimizations in modern graphics pipeline, which is just looking at the objects themselves and determining based on a depth sorting of those objects what should be drawn and what should not be drawn. That's object space methods. So for traditional raster-based pipeline approaches, for the OpenGL rendering approaches, we use image space methods. But there's all sorts of things one can do with more software rendering-based approaches that would be looking at the objects themselves and determining that I have a particular specification order of my objects, and consequently, I want these things to overlap each other in certain ways. Or conversely, removing objects by recognizing that this ball is entirely behind this cone. I really just want to draw the cone itself. Or I'm going to draw the ball first and then draw the cone afterwards. So we're painting on top of what is already painted on the scene. That's an object space method. There's also approaches, and I hope you appreciate the high quality of this image in this slide here, um, that look at which direction the objects are facing. I don't want to talk about that yet. I'm going to skip over that for now. We're going to have to talk about that later when we look at calculating plane normals and the like. But just one optimization is just to get rid of things that are on the back of our three-dimensional objects. Because if it's on the back, it should be occluded by what's in front, and so we can just get rid of those entirely. I'm gonna drop that for now because I think it's a little. It's not misleading. It's just not as important as getting to the image space methods, at least for now. So the depth sorting method or the painter's method I already just kind of mentioned. So in brief, by sorting of our z dimension of our objects, we can at the very least determine in what order they should be painted. So it's the painter's method, right? If you want to draw a three-dimensional scene on a canvas, right? A physical painter's canvas, in general, you want to start with what's going to be in the background first and make your way to the foreground next, right? By layering the paint on top of each other. In software, at least, we can do that ourselves to minimize the amount of incorrect overlap of our objects. So we have the sky in the background, and then we draw the mountains on top of the sky, and so forth, right? We can do that in our OpenGL applications themselves, because we would have, although we haven't been using that for our in-class examples at all yet, right? We would have that depth information associated with the primitives we want to draw. And that's what it's going to be for. It's how far away we want those objects to be from the scene that we're looking to draw. I'm going to say it, we haven't done it yet, but that's what that Z information, that depth information would be for. We specify that as part of our vertices, and thank you, Steve. And we um, could, on a primitive by primitive basis, sort the resulting triangles or sort the resulting objects we have to draw in our scene and just draw them from front to back. That is our so called painter's method. And again, going back to the whole point of this, I'm gonna zoom back here very quickly. The whole point of this was for a three-dimensional scene, can we have this be correct? Assume that that was the artist's intent or the renderer's intent was to have cube in the background, sphere slightly closer to us, and cone even closer to us than that. We would, in theory, then want that to actually look that way. We'd want this particular pixel to be yellow, and this particular one here to be green, and then the rest being shaded as the cube there. This approach, then, this painter's method, is maybe it sounds simple. Is in order to ensure that, well, just draw the cube first, and draw the sphere second, and draw the cone third. That's the painter's method. And it makes sense. Of course, life is not always that clean. What if we wanted to draw a cone intersecting with that particular sphere? Then this approach really wouldn't work for that purpose. But for objects that are entirely non-overlapping with each other, this approach would work just fine. And that's what this is trying to show here, that if we have our depth is not overlapping with each other, we just have a sorted order of objects. When there is depth overlapping, well, the painter's method doesn't necessarily break down, but there's certain things you can do. Just because the depth is overlapping doesn't mean the XY is also overlapping, right? So you have depth overlapping, but if the actual bounding rectangles of those individual or bounding cubes of those individual objects don't overlap, well, then you're fine. It doesn't matter which order you paint them in. The cloud is over here and the mountain's over there. It doesn't matter. They're not overlapping at all. So that's a secondary approach that you can take. Um, if you do truly have things that are intersecting with each other, then the painter's method or the depth sorting method doesn't guarantee you get a particular way of having that scene be drawn. So the depth buffer method is definitely more commonly used, and if we've used the term z buffer, or you've seen that space allocated in our driver space there, and instead what this is doing is it's not worrying about object by object basis. It's more on a fragment by fragment basis that we're computing because we're specifying as part of our input vertices. We're computing a z value, a depth value for all of the fragments that we're generating here, where we can specify different depth functions, but in general, a larger z value is further away from the camera. So when it comes time to actually determine whether or not we're drawing a fragment to the screen or not, storing it in the color buffer or not, we would then just compare. Comparing those depth values for that particular XY location and determine for this individual fragment, for this particular location, am I closer to the screen than what's currently drawn there? If I am, I should draw it. I should overwrite what's in the fragment buffer for that location. If I'm not, I shouldn't draw it. I should discard it at that point. That is the image space methods. That is the Z buffer method. When referring to a Z buffer or a depth buffer, that is a separate region of storage, generally of the same size as our frame buffer, or same dimensions as our frame buffer at least, that's storing that depth information associated with the frame buffer. And specifically for this purpose, telling us that there's something already stored in the color buffer corresponding to the scene. You've already drawn a triangle. We draw the triangle in two-dimensional, right? With x, y, with render output specifying an address for x, y in our color buffer. Now we have a new triangle coming in. We need to then check. For the new x, y values we're generating, was there already something in the frame buffer at that location? And if so, should we win? Should the screen actually display what this new triangle is corresponding to, or should we have just kept the previous triangle that's there? That has some definite advantages over the painter's method or the depth sorting method. First off, there's no sorting going on. Let's draw everything in any order, and we should get the same exact result because we have that depth information. And then it also, the other advantage is it allows us to do things like drawing a cone intersecting with a sphere in part and partially blocking and partially not being blocked by it. Because it's the individual z values or the depth values for each of the fragments we're generating that dictate whether or not that thing should be drawn. That individual fragment should be drawn. It only works for things that are being rasterized, like triangles, but that's our limitation we've already had as we've been talking about how we're drawing things in the first place, at least in modern systems with rasterization based pipelines. So that's one way of visualizing what's happening with your depth buffer method. That for the resulting ultimate XY value we're interested in, we could have multiple different primitives that would correspond to the same exact XY value. We don't have to actually sort them. We could draw this S1, S2, S3, or in any other particular order, but based on what the resulting Z or depth information, how far away we are, whether the cloud's behind the mountain or the mountain's behind the cloud, right? How far away that particular fragment is, then allows us to make that decision of should we draw that or not, or should we just discard that fragment? Don't put anything in memory based on that fragment. So it does require an additional buffer, an additional region of memory. And one thing that you tend to see is when you want to clear the background, we're ready to draw the next frame of our render, right? So we've drawn the previous frame, it's on the screen. We now want to update what's the next frame of memory to go on the screen for the next one. We would not just clear that frame, whatever our clear color is, we would do that DMA copy and clear that screen. We'd also initialize this separate buffer to some initialized value. There's different ways to do it. One way to consider it is larger from a range of -1 to 1, larger is further away. So we draw our blue sky, right? We draw whatever's farthest away to still be viewed in the scene, and that was what we would initialize our color buffer to be. That's our clear. We're also initializing our depth as well for each XY location. And then we rasterize our triangles as they come in. As we're rasterizing our triangles, right? Our triangle is what? It's vertex with these attributes. X, Y attributes gives us the setup for our equations to calculate our interpolation, our gradients for all the other attributes. We know how red, how green, how blue each of these fragments are by interpolating that information as we walk through the triangle. We would do the same exact thing for depth information. If we set z equals 0, like we've been doing for a lot of our inputs, we won't have any depth information to interpolate. We'll wind up with very flat scenes. But assume that there's some depth information. We have a triangle here, and we have a triangle here, and we have a triangle here. We're specifying that as part of our z parameter for our positional attributes for the input vertices. We interpolate that like anything else. It's an attribute like anything else. If we have 3 points in a triangle, they have red, they also have z, or depth information. We interpolate that. We then get for each fragment what the XY would be, what all the color, and then what all the Z information, all the depth information would be for every fragment inside there. And so the Z buffer method is basically, you can probably already think about where you'd want to implement that, right? When it's time to write to the frame buffer, we need to do a check first. We need to do a read, modify, write operation every time we want to write to the frame buffer. It's not hard. I just didn't want to do it already for MP1. Read from the depth buffer, determine, is my fragment that I've generated closer than what is already currently in the frame buffer? In this case, less than is corresponding to closer than. So my depth information, if it's closer than what's in there, I need to overwrite 2 buffers then. Overwrite the depth buffer with now, this is the closest fragment in the depth buffer, and it's something that's less than 1.0. And here's what the actual color buffer should be, right? Here's the actual fragment color information that I'm updating in my color buffer corresponding to that XY location and the corresponding depth associated with it. We say, less than, you could also do less than or equal to. There's other comparison functions, there's other depth ranges that you can specify, but it all follows the same exact approach, which is read from depth information first. And only if you're closer than what's currently drawn in the frame buffer do you then update both the depth buffer and the frame buffer. And that's the image space method that is used in all rasterization based systems that allows you to have three-dimensional shapes. And because again, uh, not to belabor the point too much, because it's on a fragment by fragment basis versus on an object by object basis, that allows you to draw in an order independent way all sorts of self intersecting shapes and things like that. Uh, when you're rasterizing, when you're done rasterizing and you just have fragments, it no longer really cares that it was part of a triangle anymore. It's just a fragment. It's just a potential pixel, and if it's closer than what was drawn previously, we're going to draw it. Otherwise, we don't. And all this is really saying is, given the plane equation for a triangle, we're already doing this in MP2, or at least you're on your way. The depth information, while we think of it as positional information, and it is, it's positioned in a three-dimensional space. We know that we're drawing in a two-dimensional screen ultimately, but we use that depth information as an attribute to be interpolated like anything else. And that's why we do interpolate it. That's why we grab every value to interpolate for our MP2 rasterizer hardware. We're not actually drawing a three-dimensional thing ultimately, right? It's still a two-dimensional screen we're doing here, but what we decide to draw or discard is based on what we've collected, what we've calculated for our depth information there. And um, in practice, that's a relatively straightforward thing to visualize. You can play around with that. Um, I have an example here, and maybe I'll show it next Thursday in our next lecture class. Um, from an OpenGL perspective, there's a couple state variables you want to set, but we would just want to make sure, well, depending on what we're running to render, we just would want to make sure that as we're clearing our color buffer, we're setting our background sky color. We also want to make sure that that sky corresponds to the back. So we would not just be clearing our color buffer, we'd also be clearing our depth buffer. There's various state functions that can slightly configure how we're doing our Z-based depth uh, testing. And then as we draw our polygons, we have that depth information, and it gives us that kind of three-dimensional view. I don't have this demo ready to show for today for right now, but I'll have it up and running for next Thursday's class. Let's leave things here for today. Um, I saw a lot of good progress yesterday in lab. Um, I think a lot of teams still haven't gotten to the real frustrating part yet, but you're getting closer. So hopefully you can push now and well before Monday. So the Monday is just kind of final edge case detection, and final fixes that you're doing along the way. Um, I haven't seen enough panic yet. It's coming, but get it done, get it out of the way, out of your system today and tomorrow, so that you're just polishing things up on Monday. That'd be my hope for you, anyway. Otherwise, let's leave things here for today, and I look forward to hearing from you over the weekend and into Monday evening.